Okay, this video is the first in the playlist that's going to deal with a concept area that's called solution stoichiometry. And solution stoichiometry is important in chemistry because many of the chemical reactions that are carried out in the laboratory are done in solution. And solution stoichiometry has to do with basically two things. It has to do with understanding what a solution is, and the other side of that coin is then being able to utilize what we understand about the things that are dissolved in a solution and how to use those to do calculations to carry out chemical reactions. So let me write down, all right, so we're dealing with what's called solution stoichiometry. All right, now we've already done a large series of videos in the area of stoichiometry. And in terms of solution stoichiometry, the first thing that I want to do is define basically what a solution is. Because if you don't understand that, then the other aspects of this that we're going to get into, the part about concentration and this concept area that's called molarity, is not going to make any sense. So let's deal with the issue of what a solution is first. All right, and to do that, we need to back up one step basically and talk about mixtures. All right, and mixtures are important in chemistry because they come in all different types and forms, and we utilize the properties of mixtures to our advantage in order to separate different things in order to carry out experiments in the laboratory. So first off, what is a mixture? All right, a mixture involves basically the combination physically of at minimum two different substances or components, let's call it. All right, and this issue of physically combining these things is important. In other words, a mixture is not the formation of a chemical compound. In fact, what we're doing is usually taking two different chemical compounds and mixing those together. The same way that you would take perhaps a pile of rocks and a pile of marbles, and you mix those together. All right, you put them in the same bag and you shake them up. What you've done is you've created a mixture of rocks and of marbles, and the two things have been physically combined in order to separate the rocks and the marbles. It would be a pretty easy task. All you'd need to do would be to dump them out on the ground, and literally you could sit down, and then with your fingers you could separate the two components apart from one another. Now, in chemistry, we can boil mixtures down into two types. All right, and the first type is called a homogeneous mixture, and I'll talk about what that is in a minute. And the other type is actually the one that we just described, and that is what we call heterogeneous. And I misspelled that, sorry. All right, so heterogeneous mixture. All right, now the whole focus of what we're going to do going forward here and in the following videos has to do with homogeneous mixtures. So I'm going to go ahead and get the heterogeneous mixture definition out of the way. All right, so this involves mixing substances or components that do not uniformly mix. All right, and you say, yeah, but wait a minute, didn't you put the marbles and the rocks in the same bag and you shook them up? Yes, that's true. And if you look at that mixture, you know, if you open up the bag and you look down inside of it, you're going to be able to see the rocks and the marbles. Definitely they're mixed together. However, the rocks and the marbles have basically remained as individual units, and in order to separate those things, like I said, all you need to do is pour them out onto the ground, and then you could sit down and with your fingers you could separate them. So these kinds of mixtures are unique in that the materials that you put together essentially remain isolated from one another. And other examples of this would be like mixing oil and water. All right, the classic oil and vinegar dressing, for example. You take in the supermarket, if you walk down the salad dressing aisle, you know, and you go and you look at a few of those, and you pull a sample, a bottle of that stuff off the shelf, and you look at it, and the thing you're going to notice immediately is that the two layers are completely separated. And yeah, you can shake the material up, and even if you talk to yourself, you can probably convince yourself while you're shaking that the material is being mixed together. But as soon as you set that material down back on the shelf and give it a moment or two, you're going to see that the material is going to separate into its constituent layers based on its density. The point being is that oil and water are not able to make a uniform mixture where the particles can interact and mix together in a productive way. The two materials are going to separate. Another example of this would be like hammering a nail into wood. All right, that is a heterogeneous mixture, easily separated because all we're going to need is a hammer to pull the nail out of the wood. Another example would be pizza. All right, pizza is a classic heterogeneous or heterogeneous mixture. So if you imagine ordering a pepperoni pizza, all right, set the thing down on the table and have a look at it. You can separate all the components of that mixture with your fingers. Obviously, that's going to be a messy task, but you can literally pick off the pepperonis and put them in a pile. You can scrape the cheese and pull it off and put that in a pile. Then, if you're careful with a knife, you could scrape the sauce off of it and put that in a pile. And when you're done, you're going to have the pizza crust, the sauce, the cheese, the pepperonis. Everything's going to be separated into their unique components. So basically, heterogeneous mixtures are mixtures in which the substances or the components never fully mix uniformly. Now, let's turn to the meat of the matter here, and that has to do with the homogeneous mixtures, because these are the ones that we utilize every single day in chemistry laboratories, and these are going to be the ones that are very important in high school chemistry classes, advanced placement classes, university level, general chem, organic chem, and basically all the way up the line. All right, now a homogeneous mixture is one where the components or substances uniformly mix. Uniformly mix. And these mixtures have a special name. In fact, you're almost always going to hear these kinds of mixtures called solutions. In other words, your professor or your teacher, they're not going to stand up there and go, all right, go over there and grab that homogeneous mixture of salt. They're going to say, go over there and grab that solution of sodium chloride, all right? So homogeneous mixtures are solutions. And let's go ahead and get the definition of this. A solution is, at its simplest level, going to be what we call a solute that is dissolved into a solvent. All right, now, the solute is the thing that is dissolved. The thing that is dissolved. All right, and the solvent, this is the medium in which the solute is dissolved. All right, now, your solvent is always in a vast excess. So the solvent is always in an excess by compared to the solute. And the main thing to realize is that it has to do with this uniformed mixing. So if I take sodium chloride, which is table salt, and I add it to a glass of water, all right, and stir it up, we form a solution of sodium chloride, a solution, and the solution is designated by the AQ. All right, the AQ, that's what the AQ means. So the AQ means we have formed a solution. And with an ionic compound, and I've mentioned this in previous videos, if an ionic compound dissolves, it's fully ionized in water. All right, it's fully ionized if it dissolves. That is a very important concept in chemistry regarding ionic compounds. Now, I want to come back to this uniform distribution thing. Uniformly dissolved, uniform dispersion. All right, if you look at a cup of sodium chloride that has been dissolved into water, it doesn't look any different than a normal cup of water. All right, you can't tell any difference. However, the sodium chloride that was dissolved in here is uniformly distributed throughout the entire medium. All right, and I want to emphasize the fact that if you hold a glass of water up to the light and you hold a glass of water that has had sodium chloride dissolved in it, you can't see any difference. And that's because the material that's been dissolved in there is uniformly distributed throughout the whole medium of the solvent. The same would be true if I had taken some of your sugar out of the sugar bowl and also did the same experiment. So in other words, I take some of that and I dissolve it into water, and you're going to end up with a sugar solution. Same difference. The sugar is going to be evenly distributed throughout the whole medium of the solvent. All right. Now, this distribution, all right, the uniform distribution, this uniform distribution, which I'm just going to abbreviate, is a concept that we call concentration. Concentration, which is going to be the amount of material dissolved per volume of the solution that we made. All right, now I'm going to go ahead and close here, and the next video will deal with this area of concentration.